John here. Let's look at our Z80 Retro project and talk about the I/O ports, okay? So this is a GitHub page. You can click here and you can open up the PDF version of the schematic, or you can download the project and open it up in KiCad like I have over here and have a look-see at the chips and stuff like that and what's going on in the schematic. So here is the I/O port decoder. We talked about that before. If you're following along and you missed the previous episode, scroll down on YouTube in the video description. There'll be a link to the playlist and you can find the previous episodes. If you want to interact with the I/O ports on this system, what happens is the Z80 generates an I/O request, and it is not in the middle of a machine cycle number 1. We talked about that before as well. And therefore, this chip will be enabled, and depending on the bits in the 4 bits of the address of an I/O port, remember the Z80 has a 256 I/O ports. Their addresses go from 00 in hex to FF in hex, right? Therefore, A7, 6, 5, and 4 represent the port number. This decoder here asserts an output low based on the value of the first hex digit or the first 4 bits of the 8-bit I/O port address. Thus, the naming convention down here is all the ports that start with a number 7 in hex will cause this to go low, right? So that's 70 through 7F. Any port that starts with a 4 in hex, right? Ports 40 through 4F will cause this signal to go low, and so on, all right? Let's look at this first one here and get it all on the screen at once here. The general purpose input port on our Z80 Retro board. What is it? How does it work? Why does it exist, right? This is a 74LS244, and it's our friend with the Schmidt-triggered inputs, all right? Now, the inputs on this chip, what does this thing do, right? Well, whenever this output enable signal is low, and it has 2 of them on here because it is like 2 halves. It is an A and a B. Don't worry about that. As long as both of these are set to low, this chip will copy the contents of its 8 input bits over here, okay, which constitutes these signals here. We talked about reset switch the other day. That's not pertinent in this discussion. It's only down here because it happens to share a resistor over here, all right? So don't get confused by that. These 8 signals here, which come from the printer and the SD card and this user-definable signal, which is just simply a header that I put on here, simply because I didn't need all 8 bits, and this chip has to offer. So I just said, one of them will be spare, so you can do with it what you want, okay? What does this chip do? Well, whenever this thing is enabled, the output is enabled, OE over here. What it does is it copies the binary value of each of the inputs, which the chip calls input 0A. It copies it over to output 0A. Input 1A is copied over to output 1A, and so on. Okay? So when you enable it, it takes a copy of these bits over here, the highs and lows, whatever they are, and it puts them on the data bus and sends them over to the CPU, right? I mean, after all, if the CPU wants to read the value of an input port, let me zoom out a little bit here. What does it do? It executes an input instruction, which causes the a non-M1 cycle, right? Where not opcode fetching at the point, right? When it executes the instruction, it asserts IO rec low, M1 is high. It puts the address of the port it wants to read from or do an input from on the 8 bits of the address bus, and as long as we happen to say input from a port whose most significant hex digit address is a 0, 0, 0, 0, 1, 0, 2 through 0F, this signal will go low at that time when the Z80 wants to see the value from that port. Well, that's exactly when we want this chip to turn on. And we want this chip to simply say, here, copy whatever's on these pins over here and send it out the data bus. That's all it takes to read from a bunch of wires that run over to the printer and stuff like that. Okay, so 2 of these go to the SD card, the card detect, and meso is the output line, the data output signal from the SD card. So when we write our code that says, oh, we want to exchange bits with the SD card, what we're going to do is we're going to read the values that show up 1 bit at a time on this wire right here, and we're going to do that by inputting from port number 0 over here. We'll just keep reading this. Read, and we'll watch these bits change from zeros to ones to zeros and stuff like that, and we'll read it in 1 bit at a time, okay? And we'll be getting them as on bit number D7 as they arrive, okay? Now, those of you that are really working ahead here, yeah, is there, metastability problems with this design? Absolutely there are. But I like to take a nice big step back and ask, do we care? The answer to that question is absolutely not. All right? So don't call me out on it. Why do we not care? Because when we're looking at meso, we will only look at it when it's okay and we know it is stable and it won't be changing while we're reading from it. The rest of these, I submit, no one cares, right? I mean, what is metastability really? Okay, what it really boils down to is what happens if the Z80 says, okay, I want to read this value and I want to figure out what the current value of printer error here is. Well, let's say that bit changes its value right at that instant in time. So right in the middle of reading these 8 bits, this thing changes from a 0 to a 1. All right, or from a 1 to a 0. Easily argued, the Z80 might get a 1, it might get a 0, we can't know. Why do I say we don't care? Well, what does it mean to read it while it is changing? It was 0, it's now 1, or it was 1, it's now 0. I would argue it doesn't matter which one we get at that time. If we ended up with a 1, then great. It was a 1, and maybe it'll change to 0 in the future. If we got a 0, it might be a 0. It might change to a 1 in the future. Who cares? When we read it again next time, most likely, that change will have taken place in the past, and it wouldn't matter which of the 2 values we got then. It only matters what it will be now, okay? We'll see more of this as we go. We can talk about this in the comments if it's important to you. I happen to know it doesn't matter for the kind of things that we're dealing with this port. Simply the most important one will be whether or not we're having garbage data or data while it's changing in flight from the SD card, and the software will prevent that from happening by controlling, as we will see, the clock signal such that we will only look at and use the data from this when the clock is not changing, okay? The rest of them really don't matter. The old value, the new value, who cares? Anyway, bottom line is, for those of you that don't know what metastability problems are, don't worry about it, because we'll see this will work just fine. The Z80 looks at this bus whenever it wants to do an input operation with an address that starts with a hex 0, okay? Now, here's another problem with this design. It is a real one this time. Notice that the I/O port decoder doesn't care whether the Z80 is doing an input or an output, right? Well, I don't see any read signals or write signals involved in the logic and the brilliance of this decoder over here. The only thing this decoder does is it says if we're doing an I/O request that's not, in an M1 cycle, assert this output over here based on the address, not based on whether the Z80 wants to do an input or an output, or it's a reading and writing, right? So if you decide to write to port 0, this would be a problem. The Z80 will be outputting data to the data bus, thinking that some device out there is ready to receive the data. It will assert the address as address 0, for example, which will cause this to become true, which will cause this chip to also write into the data bus. And what we create what's called a bus conflict. Both of these chips are writing. Now, it just so happens that a 244 can output, if it's trying to say, I want to output a 1 on this bit up here, D0, and the Z80 wants to output a 0 on that thing. The 244 can actually generate a pretty high amount of current. And it will win. It'll muscle the living crap out of the Z80 and force that sucker to be what it says. And the Z80 on the other end of that wire will be like, oh no! And all of a sudden there'll be a lot of current flow, either into or out of one of the pins on the Z80, which would be this one over here, the D0, okay? So if these two are in conflict, what we're really doing is causing a lot of high current to flow into or out of the Z80 in a way that exceeds the specification of what is allowed on this chip. In other words, you could wreck something. All right, now this is like that old joke. Doctor, it hurts when I go like this. That doctor tells me, I don't go like that. Okay? So, how do we fix this problem? Don't write into port 0. Only read from it. Okay? Sure. This is a self-destructive type of circuit. Why did we do that? Why don't we put more effort into this? Because it would require more gates over here. It would require more real estate on the circuit board and use more power and cost more money to manufacture and cost more power and money to use when we're running it. Okay? All because the only possibility of this going awry in that way is if we decide to do something wrong. Okay? Now, easily we can do something wrong by accident. Yes, that's true. And you certainly wouldn't want the thing to, destroy itself. Over the years, I can assure you, I have done this by accident on multiple occasions. And the Z80 is going to take a heck of a beating before it gives up and, dies. So it'll be okay to generate a couple of bus conflicts. just don't generate one that lasts for 3 years, okay? Once in a while, the Z80 will get over it. Okay, and that'll give you more than enough time to debug your code. And I'll bet if you try to destroy the Z80 by creating bus conflicts with a chip like this, it's very unlikely that you'd actually wreck the Z80. If you want to try it, whatever. It'll cost you $6 or something like that. I'd be very interested, honestly, in the comments below to hear about how long it took for the Z80 to die. Okay, if you actually do the circuit the way I've drawn it up here, and you cause that to happen, and you write, right into port 0 where you're creating a bus conflict and let it run for 3 days, I'll bet the Z80 will be fine. Okay, so enough said about that. Let's look at these other two chips down here. What are these all about? These are latches. Notice this is a 374. This one was a 244. All right. 244 is a Schmidt trigger buffer driver. All right. Which means that it just passes data through when the output is enabled. All right. What are these down here? Well, these are a little different. Notice the output is always enabled on this. Okay. Same down here. These two chips are they're wired in exactly the same way. This one has less visual noise. Let's talk about this one first. Notice this CP signal, and this little arrow down here says this is a edge-triggered clock input. A 374 is a latch. It's an edge-sensitive latch. So what happens here is when IO rec 20 over here, right, that would be this one right here, when that's low, the chip over here sees a clock pulse on on this control input here. And that happens whenever the Z80 is either inputting or outputting to port 20, 21 through 20F, right? Now this is meant for output. So it only really makes sense to do an output operation to port numbers 20 through 2F. And what this chip will do is when it sees, basically, I believe it's a rising edge on this signal, right? So when the I/O operation takes place, remember the I/O signal goes down, the I/O rec goes low, stays low for a while, and then it goes back up again. Well, that IO rec as it propagates through this gate here, right? So port 20 will go low when IO rec is low, M1 is high, and the the number on here is the right address, right? Hex 20 or something like that. Okay. When IO rec goes high at the end of the IO operation and the out instruction, okay, that's when the IO rec 20 will go from low to high, and that's exactly when we want this chip to say latch on to whatever's on the data bus at that time, right? Because it will have been given long enough to stabilize its value if it's ringing or something, if there's crosstalk between the bits as they're all shuffling around. A huge amount of time, as you recall, goes by during the IO rec cycle that we looked at in the Z80 manual, and when it goes high, these will be stable, and that's exactly when we want this chip to say, okay, take a snapshot, remember what's on these data lines, load them into a 1-byte memory latch is what this thing is, and because the output is tied on 24/7, the output over here will change to whatever the Z80 wrote into that port with the output instruction. So this is how it writes 1 byte at a time to our printer. If it wanted to write, a capital A on the printer, in hex, a capital A, I believe, is a 4-1. So that would be 01000001. Okay? And that would be, here's an A, Mr. Printer. So that's what we're going to do. When we actually print stuff to the printer, we're going to just output characters one at a time, among other things, to port number 20. All right? This chip is hooked up the exact same way, but it's not for a printer, it's for other things, right? Here's IO rec 10 instead of 20. So every time we write to a port whose address starts with a 1, right? 10, 11 through 1F, we're updating the value in this latch. Now, just like if you use this incorrectly, right, this is meant to be read from with input operations. And if you generate an output, we have a bus conflict. And yeah, it wouldn't cause the end of the world, but it's just wrong. Don't do that. What happens down here? Well, these are designed to be written to with output instructions. Well, what happens if we do an input instruction? Well, it'll still select this signal here, and it'll clock this latch. But if the Z80 is trying to read, nothing is writing onto the data bus. When that happens, these pull-up resistors over here, they're strewn around in random pins here. This is disorganized because it turns out that routing the board is easier. These are the various signals are connected to resistors in these resistor networks that happen to be physically closest to where we want them, okay? And we'll see that when we look at the board routing later, if you look into that, okay? Point is, they're all pulled up to 5 volts, so if nothing is generating any signals on that bus, they'll be pulled high. So anytime you say by accident, read from, by executing an input instruction on ports 10 through 1F, it will set all these pins to 1s. Okay? You don't want to do that. Okay? Oh, but what if you do it by accident? Your program will crash or the system can crash. Well, you do realize that any single one instruction not doing what it's supposed to do can, and quite often will, completely crash any program. All right? So it's not about trying to survive in the face of an incompetent programmer. All right? You're done. When the program's wrong, it ain't going to work anyway, and it doesn't matter what kind of house of cards it takes out when it goes. Okay? We need to be careful when we're running code on this thing. All right, so what are these actually hooked up to? Remember before when I said when we boot up and we do the, flash shadow, flash BIOS copy from the flash into the static RAM, we want to assume that all these signals were zeros? Okay, how do you think they get to be zeros? Well, one of the first things that happens in the flash startup code, we set them to 0 by doing an output to port number 10. Okay, that's how these get set to 0. Later on, when we want to interact with, you'll see this one's called print strobe here, okay? Remember, if it wants to print an A, it'll put the character A in binary over here, right? Now, how long does that stay there? It'll stay there until the cows come home and until you change it, right? So how many A's should the printer print? Well, that's what this is for. You put an A on here, and every time this thing goes from 1 back down to 0 and then back up to 1 again, it'll print 1 character, whatever happens to be coming out of this port over here. Okay, so if I put an A on the printer data port and I write a 0 here and a 1 and a 0 and a 1, it'll print 2 A's on the printer at that time. Now, I got to be careful. When I'm diddling with this signal here, I don't want to accidentally change these, okay? I also don't want to change these by accident. In fact, when I'm messing with these, I don't want to accidentally interact with the print strobe signal. So we have to be careful when we're doing this. Or again, the whole house of cards will come tumbling down. Now, while we're in the neighborhood, these are the signals that go to control the SD card. And we'll talk more about that when we write the code for the SD card. All right, these resistors are here because the SD card has to run at 3.5 volts, while the rest of the Z80 stuff all runs at 5 volts. All right, so this is a simple voltage divider. This is at 5 volts. You run it through a pair of resistors like this, and then connect this signal here up to the SD card. When this is a 1 at 5 volts over here, this is at 3.3 volts, right? When this one is pulled down to ground here, this will also be pulled down to ground. That's what a voltage divider does, okay? This is a very poor man's way of hooking a 3.3 volt card up to a 5 volt system, okay? Now, this signal here is the SD card select line. Whenever it's low, the SD card becomes active and we can exchange data. Here's the clock, 1 bit at a time we send out with the clock signal. I talked about that before. This is the data output from the Z80 or the data input on the SD card. And the card select, you remember, goes low at the beginning, and then we could send thousands of bits, however many we want, using the clock and Mosey here. And then this goes high when it's done. So what else? What's going on up here? Well, whenever the SSEL is low, that's when the card is active and we're using it. So whenever that's low, I'm going to hook it up to one of the leftover gates that we never used from up here. Oh, I can't seem to scroll correctly here. My mouse battery must be dying. Remember when we went over the reset logic here, we used these 2 NAND gates up here, and we had 2 left over because the chip, the physical chip, has 4 of them in it, all right? So what am I doing here? I'm just going to use one of the extra chips as a buffer. That's all I'm doing. That's why it's here. Doesn't really, I don't care that it's an AND gate, NAND gate, or NOR inverter. Doesn't matter. What I wanted to do is separate this signal here from the one over here, because I'm going to take this and I'm going to connect it up to an LED. LED takes a lot of current, and the output of this chip, while it can light up an LED, it might droop a little bit. And the last thing I want is if I put an LED on this signal and it's trying to set it up to 5 volts and a lot of the current is flowing through an LED, this could droop down to 4 volts or something like that, because there's a lot of load on it. An LED is a pretty big load compared to, an SD card or just some other chip, right? So you need to kind of make sure you got enough current to drive that thing, and that the current comes from something that's not going to interfere with anything else, like the SD card over here, all right? So I do not want to screw that up. So what I did is I took this signal here and just, who cares, connected it up to this NAND gate, and disk LED over here will go high whenever SSEL is low. It'll go low when SSEL is high, all right? I don't care what the polarity is. I just wanted to separate it in any way so that this current that drives this LED does not come from this latch and, parasitically drain the signal off of this thing, all right? So what actually does that thing do? It comes up way over here, and when it's high, this LED will go on, okay? While we're in the neighborhood, by the way, here's the power LED. If the power's on, this LED will go on, right? So these are the 2 LEDs on the whole board. One of them just to tell you the power's on, the other one to say, hey, we're using the disk right now. Now, if you hook this up to a high-speed system, the select line doesn't go on very long when you would use the SD card, and you might not even notice the LEDs going on. All right? Z80, very slow. Trust me, you're going to see the LED go on. Okay? When we're using the SD card, it'll be on a long time. That thing will light up. You will have no problem noticing it. All right? So that's what this thing is used for here. All right, so what else goes on with the I.O. ports? These are the discrete I.O. ports. And by that I mean these are physical, separate, single, simple-minded 8-bit latches and buffers, all right? The other I.O. rec outputs, right? So we just looked at port 0, 10, and 20, and we know that 70 resets the reset circuit, right? Or sets it, as you might think. All right, what about this 30 and 40 over here? Where do those go? Well, this one, what is this, 30 over here? This is 40. 40 goes over here. This is the counter timer controller. Well, the Z80 comes with a family of chips. Here's the CPU, we all know and love, hopefully, or will by the time we're done with this. This chip over here is a serial I.O. controller. All right. That is a Z80 specific peripheral chip. It's part of the family of chips that Zilog makes to go with their CPUs. And this is what we call a counter timer. All right. Now, back in the 70s, we couldn't put a lot of stuff on one single chip. Nowadays, you buy a system on chip, even an Arduino or something like that. The chip has, memory, it has flash ROM, it even has counter timers, and it even has a serial port and SIO, SPI, I should say, ports and stuff like that, all on the one chip. Z80 doesn't have that. It doesn't have any boot ROM, it doesn't have any RAM, it doesn't have any timers, it doesn't have any serial controllers, and it doesn't have an SPI. We need to provide all that externally. Okay? So this is just simply only 4 counter timers on one chip. And if the Z80 wants to configure the counter timers and start it and stop it and tell it, oh, I want you to count at this speed or whatever it's going to do, it needs to do an input or an output operation on port number 40, or more accurately, any port that starts with a 4 in hex. Okay? Now let's look closely at how this thing is connected up. Some of the stuff over here has to do with, these are the clocks, right? The master system clock here, that'll be running at 10 megahertz. The baud rate clock, we'll talk more about that when we get over the SIO, okay? What happens is this clock, these counters, count at different rates. What's the rate at which it will count? Well, it'll count at, if we hook it up to this, 10 megahertz. Which I, off the top of my head, just realized is probably not even legal for the counter timer to run that fast. This is probably a design mistake. It doesn't matter. We just won't use it if it's counting too fast. My point is, and the reason I'm laughing is it just dawns on me that I believe that the rule for the counter timer is that these clock inputs must not run more than half the speed of the system clock. So doing this doesn't make any sense. It's okay that it's there, but we can't really take advantage of it. If you want to count at the 10 megahertz system speed, you can configure the chip to do that. All right, so I'm just laughing at myself. This is a design flaw that really won't impact us at all, really. We can change it if we want to, but it turns out these become unused, just like the other X'd out pins over here, right? The main reason this is here is so that we can divide the baud rate clock down if we don't want to run at the maximum baud rate, which as designed, this will run at 115/200. If you want to run at 9600 or 2400 or 300 or even 50 baud, you need to divide that clock down. And that's what we're going to use this thing for. All right. So how does that happen? Well, the Z80 comes along and it says, all right, I need to set a bunch of values in the various registers that are in this chip. So what it's going to do is it's going to write to address 40. And look at this. It's also got A0 and A1 coming along in here. Right? Remember, the I/O decoder ignores A0, A1, A2, and A3. It only looks at 4, 5, 6, and 7 here. Okay? Therefore, when IOREC 40, which we connected up to the CTC, is low, it means that this chip is enabled and told, hey, the Z80 wants to change the value or see the value of one of the registers that are inside here. Well, which register is that? It's the register whose number shows up based on A0 and A1 over here. So in this case, while the chip is enabled for all I/O ports that start with a hex 4, which register is going to be written into or read from will depend on these 2 bits in the address. In other words, address 40, 41, 42, and 43 will access 4 different registers inside this chip. And those 4 registers represent each of the 4 different counter timer clocks that are in here. All right? It's as simple as that. Remember earlier when I said we have to be really careful about weird I/O requests that take place during machine cycle 1 in the Z80 system design? There's a private little dialogue that can take place between the CPU and the peripheral. That's why the CTC, and as we'll see the SIO, wants to catch a glimpse of M1 and IOREC independently of this chip enable over here. Right? Because remember, IOREC 40 already depends on IOREC and M1. IOREC 40 can go low if and only if M1 is high and IOREC is low, which is the data transfer of an input or an output instruction. Okay? The CTC wants to be able to also know when M1 is low and IOREC is low, which takes place at a time when this here is not low. Okay? That's when the Z80 is initiating a private conversation with one of its custom peripherals. Okay? So, notice also that there's a read signal involved in here. The CTC supports independent reading and writing of its 4 registers in here. So, while IOREC 40 goes low to enable it, to assert the chip enable as true, without any regard to whether it's reading or writing, it needs to be told which way to move the data. So that's why read is in here as well, okay? And that pretty much covers all the pins. We'll talk more about all this stuff and laugh some more about this foolish choice that I made over here when we talk about how to actually program the CTC and why this is probably a useless signal to use on the CTC. It turns out in this design, there's really nothing else to connect it to. Feel free to leave comments in the notes below what we might want to do with that. I suppose I could hook up another header on the board or something so that there'd be pins and you can connect them to something else if you really feel like it. Otherwise, it doesn't really matter because there's nothing on the board that I'm aware of that would be otherwise interesting to count using this circuit here, okay? Now, if we go over to SIO, we'll see the same games going on. Where are the magical pins? I think they're over here, right? Here's our IO request, and it enables the chip just like the other one. We'll see here also this one wants to know when there's a reset signal, by the way. I think the CTC also gets a reset in it somewhere. Yeah, it's over here, okay? As I said before, while the Z80 can take the reset right from the capacitor and so on, these probably do too, since they're all designed in the same family. But this is an example of, keep your eyes open and understand that this reset signal is going more than just to the Z80, okay? In fact, if you sent the reset signal to this gate up here, This thing here might also have a problem with it. Okay, turns out it's got a Schmidt trigger, so technically it would not, but it's used all over the place. Some of these circuits might be more concerned about a clean reset signal than the other ones. All right, so yes, the SIO and the CTC need reset. They both look at M1 and IOREC independently, and they both have readable and writable registers. So this game over here with the reset M1, this is the same situation happening with the CTC as with the SIO. We also see A1 and A0. All right, they give them different names, but it's the same situation. This has four different registers in them that can all be read and written. So just simply enabling this chip is not as useful as it is when we were down here and we just blindly enabled the whole latch. Okay, there's only one thing this latch can do, and that's what it's going to do. So it really doesn't matter that we don't have the read and the write signal involved in here. Okay, yeah, if you do an in when you meant to say out, or you say it out when you meant to say in, the wrong thing could happen. And yeah, we could have a bus conflict up here in this situation, but there's nothing, it's not going to be any major physical problem. This one is with the CTC, it just simply needs more information. That's why the other bits are in here, okay? And that's how these guys are all hooked up. Obviously, the data lines in there to exchange data. These over here are all the pins that deal with the various signals. And this thing is a serial port controller. Okay, these signals here end up going down to the circuit that's down here. This is the RS-232 voltage converter. So we can hook up, genuine, bona fide RS-232 devices. These four signals over here go out and around from the SIO that we were just looking at. This thing converts the voltages to the right values for RS-232. There's some jumpers over here and a connector so you can plug in your terminal. All right. Now, these jumpers are here so that you can switch around whether you're, transmitting or receiving on which pins, all right? I find that so annoying. You never have the right cable when you're doing RS-232, and it's just never right. So I put a jumper right on the board. You just move these jumpers back and forth, and it reverses the meaning of whether or not pin 2 transmits and 3 receives, or 3 receives, all that. It just switches these two around, okay? We'll see more about that when we play around hooking up a terminal on the serial ports later on. All right, but that's what this thing is doing here. Okay, this is stock off the shelf part, been around for 30 years. Just simply slap it in there and take care of your voltages. All right, so that's all the I/O ports. All right, basically we've talked about every single thing that's in here so far, other than the power supply, I suppose. The short of it is, look, there's a voltage regulator, okay? Turns out this particular voltage regulator generates the 3.3 volts that we need to operate our SD card. Okay, see the V33? That comes with the voltage regulator above. The 5 volts that runs the board as a whole just comes directly from the USB connector that we hook up to power only. Right? There's a power only USB connector, as you can see here. We hook up ground in 5 volts, and the other shield ground, we ignore the data lines here. Power the board only. Okay? There's some cuteness going on over here that has to do with the printer. We'll talk about that when we talk about the printer driver. The short of it is, these act just like that the NAND gate did. These are just simply buffer drivers, okay, that allow us to send signals out of this chip without running them naked off of the board. We use these chips to hopefully increase the power on those signals, all right, which may or may not help, but had extra gates, and that's what I used them for. Back to the SD card here. This is powered by the 3.3 volts. You see the SSEL, MOSI, clock, MISO, and the DET. These all go to those general purpose I/O pins that we saw on the latches. We'll talk about how to use all these signals when we write the driver to talk to the SD card, okay? Short of it is, these are the 3.3 volt signals going in and out of the SD card with a 3.3 volt power. This resistor here is, according to the SD card spec, we have to pull that up to 3.3 volts for the data coming out of the SD card, okay? That's how this thing works. Now, this is a socket that's not super easy to solder onto the board. If you don't want to do that, instead of this, you can just ignore all this. Don't even put it on the board, and instead hook up a SparkFun DEV13743. It's a board that I've pinned out this connector right here. It's got all the same signals, and these signals are the 5 volt versions of these 3.3 volt signals over here. Short of it is, stick this header on your board if you don't want to solder in an SD card. Or you tried and you failed, throw the board away so nobody sees it, because if you're going to order your boards directly from Shenzhen anyway, you're going to get 5. You can always throw one away. Just don't tell anybody, okay? And if that happens and you can't get it to work, just solder in J10 here and go to SparkFun and buy a $5 adapter board, stick that on here, and you're done. It has its own 3.3 volt regulator and power and all the other stuff, and the jack is on there. And this is just a simple 0.1 inch header that anybody, if you can solder in anything in a through-hole board, you can successfully solder in one of these, the connector for this thing, okay? What else did we not talk about in here? This giant connector here is just 1-for-1 the same pins that come off the Z80. All right, I put this on here for 2 reasons. One, it's easier to clip a little probe onto one of these pins that come off a header than it is to try and clip it onto the pin off the chip. And number 2, this big old connector is going to be where we hook up our flash programmer, and we're going to take over control of the bus by asserting the bus request signal here. And we're going to steal the bus away from the Z80. And once we have it, we can then generate signals to the flash. We can assert that, hello, we're going to enable the flash, we're going to generate write operations, and we're going to write the magical configuration to enable the flash to become into programming mode, and then we can just set the addresses to whatever we want, set the data to whatever we want, and assert the right signal to pulse it to store data in the flash. That's how I'm going to program my flash. If you want to, you can buy a standalone flash programmer and take the chip out of the board, put it in that programmer, program it, put the chip back into the board every single time you want to update your code. That's fine and dandy. That's the good old way. If you really want the traditional experience, you'll do it that way. I'm too lazy. I'm going to just design a $2 board that you can order along with this one that allows you to just hook this connector up to a Raspberry Pi, and you can do the whole thing in circuit while the system's running. The Pi can pause the Z80, sneak some new code. Gee, this mouse is going nuts. Sneak some new code into the flash chip, okay? And then reset the Z80 and let it go again and start it over again. You can go through that kind of a development cycle, which admittedly is a little bit more like how you would do it on like an Arduino or something like that. Okay? This connector here is for the printer. This is pinned out very specifically to match if you put a ribbon cable in this connector header on the PC board. This will match exactly the pinout of an IBM PC parallel port in a DB25. At which point, you can just go to the store and get any old IBM PC port, DB25, adapter cable for whatever printer you want to use. And any printer that's ever been manufactured that has a parallel input port on it, you know, after 1980, okay, has an adapter cable for an IBM PC. So you don't have to worry about any of that malarkey. If you own such a printer, odds are you probably also own the adapter cable for an IBM PC, okay? That's why I pinned it out this way. If you don't care about this fact, then that's perfectly fine too, because it doesn't matter to you. You make your own cable and do whatever you want, all right? I guess we can comment quickly on this again. I mentioned it before. Notice that some of the pins from the SIO, right? This is the SIO over here. Namely, the request to send and the DTR, data terminal ready bits, that are outputs from the SIO. Look what I did with them. I ran them through these gates, and they're connected up to the printer. Well, it turns out I didn't have enough I/O ports, or in this case, output ports, on these chips down here to run the printer. The printer needs, it doesn't need them, but it has an initialization signal, and it has a, what is the other one? Oh, a line feed control signal, all right? This is the line feed and the init signal. It even has another one called select, all right? But I've permanently grounded that. So if you plug in your printer, it's selected and it should be enabled to run at all times. I don't do this in my BIOS, but you can if you want to. You can set this signal low and then back high again, which will reinitialize the printer. And if you got a super fancy printer, maybe it's stuck in graphics mode or something. This would be a useful thing to be able to do when the system boots, because by definition, your computer may not realize that it's in some wonky mode. This signal up here, by definition, tells the printer that every time you print a carriage return, the print head goes from right back to the left margin over here. Should it automatically advance to the left to the next line when it does that or not? Okay. Normally, you would not have the printer do that. Okay. You would want to control that. And the reason you want to control that is so you can overstrike, right? If you wanted to print a line of text and then go back and do like a strike through line, the way the printers oftentimes would do that is it would print a whole line of characters, then it would do a carriage return and assume that the printer would not automatically line fade. And then it would print a bunch of hyphens through all those letters. It would just do a 2-pass, okay? Then it would do another carriage return, and then it would manually send a line feed out. All right. So for whatever reason, in the 70s, we had for when this was created, the spec was created, they decided to allow this to be a configurable thing based on the computer. All right. The rest of this is somewhat straightforward, I think. We already talked about print strobe and the data lines. Down here, these lines have to do with, when the printer says, okay, thank you very much, I saw that strobe, and I'm going to print that character now. Down here, it says, I'm kind of busy right now, stop sending me data because I'm going to overflow my buffer. This it gets asserted when the printer runs out of paper. And to be honest with you, I cannot remember for the life of me right now what this is for. So I'm going to let that one go and kick it under the rug until we get to the point where we talk about our printer driver. At which point, the printer status signal, whatever that represents, might be relevant. Okay? So what do we got here? Why then did I hook all this up over here? Like I said, I ran out of output ports on the general purpose latches, and I'm going to use these. And what that really means is we got to ask the SIO to set these values for us, which is kind of wonky out in left field when we're dealing with a printer driver and we have to interact with a serial controller to make that happen. This kind of thing is very common back in the old days when people didn't want to put, additional chips into their design, increasing cost and stuff like that. It's easier to increase complexity in order to simplify the hardware. This is always the way you go, okay? Now, why didn't I use this in my serial port? Because my serial ports I configured to be what we call 3-wire interfaces. If you look down here, these thingies only have 3 signals on them. Ground, and these 2 pins here are like transmit and receive. There's no hardware handshaking in this design. Okay? It turns out that the SIO is kind of weird when it comes to hardware handshaking anyway. This is kind of more designed to be, this is more useful with its additional signals over here, in my opinion, when it's operating in synchronous mode, rather than when it's operating in asynchronous mode. I'm only going to use it in asynchronous mode here, okay? At which point in time, these signals are, whatever. You can use them if you really want. If you plug in a modem, it'd be nice to see if the ringer, if the ring detect signal and stuff, that's the kind of thing you might see hooked up to these other pins. But I'm not going to do that. Mostly because while I do have modems, I don't have any phone lines to plug them into. So I don't really care right now. And besides, if you remember how the Hayes character set or the Hayes control protocol worked, the modem also prints the word ring when the phone is ringing. So you don't really need that wire. Okay, it can and does send you other interactive clues to what's going on the phone line anyway. And you can use that if you really want to know if the phone's ringing. Okay, so let me know in the comments below if you prefer otherwise. When we look at the innards of the SIO, I'll tell you why I'm not too happy with how the handshaking really works on this when it's operating as a serial port. And since I don't like it anyway, it's a perfectly reasonable thing to do to use these extra output bits for other purposes, all right? I have those output bits that I've hijacked and connected to the printer. These are input bits that have to do with synchronous mode. and I just didn't connect them. There's nothing to do with them. Down here, what do we got? We got more output bits. I didn't even use these two. Again, comments below. Should I hook these up to some headers? Did anybody think of anything cool to do with these? And these other inputs that we don't use, I just connect them to ground and say, oh, they're off. Here's some more inputs that I don't use, right? That, again, have to do with synchronous mode, all right? And now what have we done? Have we finished everything? We actually have, except for the clocks. Here's the easy one, the system clock. Right? What is it? It's a little metal can. You put power on it, and it outputs 10 megahertz. Any questions? All right? That's the thing that runs the Z80 clock and the peripherals right there, okay? And if you want, you can take this out. I put a socket on the board. You can unplug it, and you can plug in another one. Maybe, like, for example, I couldn't find a 10 megahertz chip when I first started this project, and I said, well, golly gee, good thing I put a socket on here. I just stuck in a 6 megahertz oscillator instead, and you can just change the speed of the Z80 to suit your needs. This other clock, okay, this is for the baud rate. I chose to pick a 1.8432 megahertz crystal. Seems like an arbitrary choice, unless you are familiar with serial ports. It turns out this is a very standard speed because it's an even multiple of 15200 baud, which is the kind of like the universal kind of highest speed RS-232 type of speed you normally get. 115.2 equals this divided by 16. And when we program the UART, we'll see why that's relevant. These jumpers over here are in the circuit because I want to be able to either connect this crystal output, this clock output, directly to the SIO if I want to. So where it says SIO clock A and SIO clock B over here. Those signals go into the SIO somewhere over here. Where are they? They're probably over here. SIO clock A is right here. And those connect up to the receive and transmit clock inputs on the UART over here on the SIO for port A. And that's independent of the clock that goes into port B over here. All right? So we can run each one at different speeds if we want to. And if I want to, I can put a jumper between pins 2 and 4 and another jumper between 1 and 3, which will connect this clock up directly to the SIO. Or I can move the jumper down here and connect 3 to 5, and look what's happening there. I'm connecting the clock that goes into the SIO, which is this signal here, and I'm saying get it from the clock B output on the CTC. Same thing for the port A on SIO. I have another CTC channel for that, okay? So we can either run the clock directly into the SIO, or we can say get the clock from the CTC. If we get the clock from the CTC, it comes from these pins over here. One of the inputs to the CTC that do make sense, at this point I'll point out, is the baud clock oscillator that we saw above. We can simply use the CTC to divide that frequency into another frequency that runs slower, okay? So the CTC can divide it by 2 or 3 or 4 or whatever and slow it down, all right? So we'll use the CTC if we want to run at slower baud rates, okay? That's why this is hooked up the way it is. That's also why I never noticed that I did something foolish here. I just simply hooked it up without thinking, and I have yet to use it, so oopsie. Again, comments below if you can think of anything creative to do with the extra ports on the CTC. One of the things that I do with the CTC, by the way, is I hook up, I don't remember if it was port 0 or 3. You can tell the CTC to take clock number 3 or whatever, any one of them, and use the system clock, in this case it's 10 megahertz or whatever, and use that as the timing source and divide that down by some value. And what I did is I just divided that down by I don't remember what to slow it way down, and then I can tell the CTC to generate interrupts over here to the Z80 so that every now and then, maybe 100 times a second or something like that, it will interrupt the Z80, and the Z80 simply counts every time that happens, and it keeps track of the time that has passed since the system boots. This is my uptime timer in that scenario. All right, so you can do whatever you want with this sort of thing. All right, so with that, I think we've addressed all the parts in the schematic. Now it's a matter of what do we do with this thing? And that all puts us into the realm of software. So next time, we'll start trying to start this thing up by writing the flash code. Till then, thanks for watching. See you next time.